Okay, I'll get started with the class since it's 7 o'clock. You guys can maybe follow this video lecture later if you need to refer to it. Um, so, like since the last 9 weeks, we have been learning about deep learning and the different classification tasks, and even more interesting other tasks like object detection and so you got to learn like in object detection. Probably there you got to first, get an experience on how neural networks like perform regression because you need to predict the bounding boxes as well, so regress through them. So basically, till now we have been seeing many of the supervised tasks. So remember that supervision needs some labels, or it needs either. I mean, if those labels are like discrete, we call it classification. If those labels are um, continuous, we call them regression, right? So this is probably the first time that we'll properly touch upon the unsupervised area. And let me share my screen first. So, okay, just give me a second. Yeah. Okay. So I hope that the screen is visible. So today we are going to talk about something which is not only unsupervised, but it is one of the central building blocks of deep learning. This is where all the wonders of deep learning comes into existence. And this topic has become the thesis topic of many masters and PhD students. So yeah, it's very interesting to follow. And so the recent most advancements that are there in this field, in this area, they are like tremendous. So also another thing is that research on this in this direction is still pretty much ongoing, right? So a lot of it is, I mean, people can do a lot of things, but another, I mean, they also can't do a lot of things. So there's a lot of options here. So you can leverage that and make this part of your thesis if you are interested in pursuing higher studies. So yeah, so week 10 is about generative models, like I said. Um, so, what is the goal here? Goal in discriminative tasks, right? So, discriminative is what we have seen till now, right? So, the classification or the regression parts that we have been talking about, the regression tasks that we have been talking about, so they all fall under the discriminative models, okay? And so, just to give an example, what would that constitute? So you have been given some data D with data points as x1, y1, x2, y2, and so on until suppose x and yn, right? So what do we model in both classification and regression setting? We need to learn a function from this x to the y, right? So we need a function that can approximately generate all the y's given the x's, right? So that is why we use the training. For that, we use the training data basically. And on a test sample like this X test that is given here, hope my cursor is visible. The task is, so this is unknown. For this, we do not know the label from beforehand. The task is to predict the Y, right? So this Y can be continuous or um, it can be discrete. So if in case of binary classification, basically what we do is we want to learn a hyperplane between these two sets of classes, right? 0 and 1, the red and the green, right? So this is what we are trying to do in discriminative model. So this is what we have exactly seen throughout all these weeks, right? So yeah, I mean, the point to be remembered is that you are given the labels right? Or yeah, or you are, I mean, the labels can either be like discrete or they can be continuous. And your job in a discriminative setting is to learn a function that can approximate these y's given the x's, right? So this function f is what we are after in all the discriminative cases. Cool. So now what about generative? So how are they different in generative modeling? Right? So in generative, notice that we have defined it here. So like in discriminative, we do not have, we have the x's and the y's together. So x1, y1, x2, y2, and so on. In generative models, it's a little bit different, right? So in the generative models, your given data is just x1, x2, xn, right? There's no concept of y's, which is what makes it unsupervised, right? Now, given this, what we want to do, given this x1 to xn, so in the generative models, we are not trying to cluster anything like explicitly, or that, I mean, the way we actually understand the unsupervised methods. Here, what we are trying to do is, given these few samples of data, we are trying to model, or we are trying to understand the underlying distribution which is written here, right? So we are trying to understand this p of x, right? Given these given this may be limited or finite sample of training data, finite samples of training data, we are trying to learn the underlying distribution, right? So that what we would do is, if we get to know the distribution of the training data, then we can use this to sample more examples, right? So we will sample some, maybe x dash 1, x dash 2, x dash 2, x dash 3, and so on, dot x dash 10. So all of these x dash 1, 2, 3, and whatever, they will be like very close to this x1 to xn, but probably not exactly similar, right? So how will they help us? So if we are able to do something like that, if we are able to understand the underlying data distribution and then sample more data points from there, that means what? That we will be able to detect, or we will be able to generate new and new images. That is why, that is the goal in generative models, right? Now, what is the problem in this? So, all of these first two lines, they look very neat, and they define very clearly what we need. And if we have what we need, what we can, the power that will come to us, right? So, if we have access to this P of X, we can generate all different sort of samples, which will be different from the training set. So, that will give us power to generate. However, the loophole here is that your you are given, suppose your training set consists of, suppose, 1 million data points, right? Even then, you are given only 1 million data points, right? To mod And your data dimension is extremely high, right? These are all images. So from those 1 million data points, it's not easy, it's not simple to predict or find out what the p of x is. In fact, it is impossible, right? So there is a true data distribution, right, from which these data points are already being, they have already been sampled, right? So like I said, it's our job to find out what this distribution is. But given that we have only access to maybe 1 million data points, where each of the data points come from very high dimensional data, it is impossible to find out what this correct p of x is. Okay, so, what do we want to do here? So, the whole job of neural network, as in discriminative and generative, is just one, that we want to learn an approximate function. Now, what we want to approximate through that, that is dependent on the application that we the application that we want to take up, right? So, if it's a classification task, you would want to learn a function that maps your x to a y, right? So the that function will not be exact, but it will be like a pretty good approximation of the true function. Similarly, here also, Here, the necessity is not to predict a y. We do not have a y here. We are trying to generate new data, right? New samples given these samples, right? So here, since we do not know the true data distribution, what we can do is we can have some parameterized density model P of theta, where the parameters are given by theta, right? This we can have, and this we can make sure that it's as close to the true data distribution as possible, right? We do not know the true data distribution, but we want this. I mean, ideally, what we want is this should be as close to the true data distribution as possible. So basically, we need to select the parameters in such a way that this distribution p theta moves towards p of d, right? As close as possible. That is what we want to achieve in this particular exercise, right? So we do not have access to the true data distribution, which is given by this PD or this thing. Um, and we want to approximate it by a parameterized distribution P of theta, where the parameters are learnable. So we want to learn the parameters in such a way that this P theta is as close to PD as possible. Okay, so have a couple of questions here which will probably help us in um, learning the concepts a little bit better. Okay, just give us a second. Yeah, all right. Yeah, so let's go through this question once. Okay, is there something? Yeah, right. Okay, right. So let's go through this part once. Okay. So this question, in generative modeling, if one chooses to use scale divergence to minimize the distance between the unknown true distribution P, oops, and the approximating distribution Q theta. So different people, there are different notations to denote all of these, right? So there's an unknown distribution P, I mean unknown and true distribution P, and the approximating distribution Q theta. So the problem of learning the true distribution simplifies to what? Right? So the answer is already marked here, right? So all of these are the options that you have. The answer is marked here. Just wanted to go through the solution once so that you know how to find these solutions, right? So what you do is, what have they asked? So you start with that, right? So they are saying in generative modeling, if one chooses scale divergence to minimize the distance between the P and the Q of theta. So then why not just write down the formula of like this scale divergence, right? So what we want is we want this loss. This is what we want to minimize, right? So your the distance between your data distribution and the uh, approximate distribution should be as low as possible. So by the way, Kale divergence and J's divergence, so all of these are basically functions that calculate distances between two distributions. Okay, how far away are the two distributions? That is calculated by this Kale divergence loss. So what we are saying is that we have a true distribution and we have an approximate distribution. And in the question, it says that we are choosing the Kale divergence to minimize this particular distance. So this is what we want. Okay. Now we'll break this formula, right? So here we have approximated this formula a little bit, right? So if you go to the loss function of, sorry, the exact formula of Kale divergence loss, you'll see something like, so D stands for the true data distribution and theta stands for the approximate distribution. So this is the formula for Kale divergence with just one problem that, I mean, outside the log also there is a term, there's this PD of X term, right? So we can ignore this at this point because it doesn't really matter for our minimization. So our minimization only involves theta. So it only involves the terms that have this P of theta. So since this PD of X, I mean, in the normal Kale divergence loss, it's generally outside also, right? It's PD of X log PD of X by P theta of X. But since PD of X is independent of theta, it's okay to not consider it, right? And basically your um, this thing is you approximate this or you minimize this for all the data points that you have, right? So now, like I said, that the outside term we can ignore already because it doesn't have the d factor. It doesn't have any theta factor, right? So now you break this log up. So this becomes the first term becomes expectation of log of p data x minus expectation of log of p theta x. Again, we are minimizing with respect to theta. So the first term can be ignored completely, right? So we have a um, um, yeah. So our objective is to minimize based on the theta. So we throw away this first part and we only have this second part. Okay, so finally it becomes min of theta. We have had this negative sign outside. So now in expectation, since expectation is a linear operator, so it's okay to move this negative sign inside. So it's the expectation of minus log of p theta of x, right? So now the point to be noted or the point to be remembered here is that okay, so you have this minimization side, okay, on the outside and a negative on the inside. Okay, so what does that mean inherently? It means that you are trying to minimize a negative, something negative, which also in some sense uh, points to something like a maximization. Okay, so you are trying to maximize this quantity when you take into consideration this negative and this minimum and this negative. If you take them together, if you take them outside and take them together, this becomes maximization of E of log of p theta x, right? And that is basically what is maximum likelihood estimation, right? So this is the likelihood and you are maximizing it, log likelihood. You are maximizing the log likelihood. That is why you are, it says that this is basically simplifying to identifying parameters by maximum likelihood estimation, right? So in this kind of questions it's always wise to first whatever it's written or whatever is asked for in the question, just take that and write down the formula and try to simplify it in the terms of like linear algebra or probability. And once you are able to do it, you are done, right? You'll be able to simplify and find out the answer. So for example, like here we saw that if we take the minimum and the negative, we can convert it to maximum, and that gives us the formula for the maximum likelihood estimation, right? Hence point number one becomes the solution. So we just wanted to show this how this is done exactly. Okay, now this is very simple. So given an input x and an output y, which of the following is the quantity of interest in discriminative modeling? So again, if we go back to discriminative modeling, what did we want? So we had some data x1, y1, x2, y2, and so on, and we wanted a function that would predict y for us for an unknown test data. Oops, sorry. Yeah, so, out of these options, that is why I'll mention from beforehand that this option is the correct. This is the correct answer. So, given an input x and output y in the discriminative modeling, you are after y. Okay, so you want to learn the posterior distribution p of y given x. Okay, so yeah. So all you need is you want to find the you want to learn a function between x and y in the training data, and in the test data you want to find y given x, right? Hence, the last option becomes the correct choice. Okay, so yeah, whoever joined, so I actually started with the class because it's pretty late. So please follow the video in the initial part, so to cover whatever I have talked till now. So basically, to summarize, we have gone through what is discriminative modeling, what is generative modeling, and just to give a background on, because this section this week is on generative models. The background is that. In generative models, so it's not a supervised task anymore, so we do not have the labels y, right? So all we have is some data points x1 x2, so these are all images, we can think of them as images. So x1 x2 dot 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 xn, and we are trying to learn the distribution that generated these x's, right? It's impossible to learn the true distribution because you would need infinite number of samples which you do not have access to. So as in deep learning we are always trying to approximate, here also we are trying to learn a approximate distribution which should be very close to the true data distribution. So the idea is that if we have access to such a distribution which is very close to the true data distribution, we can just sample more points from that distribution and that will help us generate new points. Hence the term generating models. So yeah, so we were going through two questions which can be referred later in the videos. Um, but yeah, let's have a quick revision of the generative adversarial networks. So we know that nowadays, if I don't know if you're aware of it, but diffusion models are out there and they have pretty much uh, swept everything in the generative scenario. But for 20, till 20 from 2014 till at least 2020 or 2021, GANs were the de facto standards for generating new images in various ways. And even now, multiple researchers are still working on generative adversarial networks. So the way that we remember GAN is through this picture, which is very popular, right? So here, adversarial, the term adversarial basically refers to some sort of a like min-max game that goes on between two adversaries or two opponents, right? So just uh, remember it in this way that suppose there's a thief, right? So there's a bank, first of all, that is able to give you or generate some real currency, real notes, currency notes, right? And now there's a counterfeit fraud, which is the generator, which is like a thief. It's trying to uh, counterfeit or maybe it's trying to generate some fake currencies, fake notes, right? So like we see in the market very often, right? So it's trying to generate fake notes, and now there's a police, right? So there's a cop which is whose name is discriminator, and he is trying to basically find out that given these two notes, what is the real one and what is the fake one. Okay, so this is the game that is being played. Now initially the thief doesn't know anything about what the currency note looks like, okay, or he doesn't know how to copy them, right? So copy the real notes, I mean. So what he'll do is he'll try to create something which is not a very good approximation of the real money, right? And now he'll get caught by the police, right? So now next time, this will tell the generator or the thief that okay, the currency that I created, the note that I generated was not good enough. So now he'll improve the quality of the fake note, right? And he'll go on doing this iteratively until the discriminator is now confused, right? The discriminator is not able to say that given this and this, what is the real and what is the fake, right? So the generator's job or the thief's job is to confuse the police, right? And the police's job, on the other hand, is to carefully detect what is the real one and what is the fake one, right? So this game sort of that goes on this adversarial yeah, game between two different opponents that goes on is what is the foundation for generative adversarial networks, right? So you imagine it this way, that if we come here now, right? So what do I want as a function of the generative model, that it should generate new images for me, right? Now it's not, like I said, in without access to the true data distribution, it is not at all trivial to generate new data, right? So how does this particular like the GAN model work, the principle behind the GAN model? It works in this way, that you have a generator, okay, which basically learns a mapping from a noise distribution to some image, something some distribution in the image space, right? And you also have the real training images, right? So you have the discriminator here, where the discriminator's job is to say that given these fake images, so the generators generated images are always the fake images, so they are the fake currencies, right? So it's the, like the name suggests, the generator's job is to generate the new images. We are calling them the fake images. Um, and we also have the images from the real training data, and discriminator's job is to classify these two. So it should be able to classify this as fake, it should be able to classify this as real, right? So ultimately what we want here is that, like here in this case, the like, when will the thief win? The thief will win if the police is, if he creates so realistic looking currency notes that now the police himself is confused. The police is unable to say whether a given currency is real or fake, right? Similarly, for GANs, it's the same thing, that the generator initially will probably generate something very bad, right? That will be very easy for the discriminator to identify. But now the generator will keep on improving itself, right? By looking at the discriminator's abilities. It'll keep on improving itself, which will make sure that the fake images get better and better with time, until a time comes when the fake and the real images are not that distinguishable, right? So that is what is the moral of the story in GANs, right? So we'll quickly go through the training objective also. So we have two things here, right? The generator and the discriminator. So both have their own agendas. So the agendas are pretty opposite of each other. So discriminator wants the images to be correctly classified. Generator wants to confuse the discriminator. It wants to generate fake images in such a way that the discriminator is no longer able to distinguish between these two. Right. So now, so like I said, I began I think it's easier to explain it in terms of the discriminator first. So like I said, its job is to classify these images as correctly as possible, right? So now look at it in this way. So just remove this min of G part, right? Just look at the max of D. Oops. Yeah, the highlighted part, just look at that. Okay. So what does the discriminator want? So for the images that are there from the training data that are generated from, I mean, basically for the training images, they are the real ones, right? So now one thing that you have to do is, for the training images, in order, so the discriminator is just a classifier, right? It's a binary predictor where it will learn to predict this as real and this as fake. And so, like we generally label our images, so real is labeled as 1, fake is labeled as 0, right? So now see, so what it will try to do is, it will try to maximize uh, like whatever it predicts for the real images, that should be as maximal as possible, because it has to predict 1 for the real images. So that is what is given. Oops, sorry. Yeah, that is what is given in the first term. That for the true data, for the actual data, my discriminator's output should be as high as possible. Hence this max D and this first expression. Similarly, it is not enough to just do this, right? So I have to make sure that the fake images that are, so if I am the police, if I'm getting the fake images, I should be able to catch them very properly. So the fake images, for the fake images, the discriminator output should be as low as possible. And that is just modeled by this second term. Oops, yeah. So basically, so here now, instead of taking the true training data, we sample some Z from a prior distribution, that is the noise. And what I said is, the generator basically is a, like converts this noise vector to a image, so to something in the image space, right? So what the model, so you can see that now the D, previously the D was taking into account the input as X. Now the D takes the generator output. So the generator output is given by G of Z, right? Z is the latent vector, latent noise, right? So D of G, so this D of G should be as low as possible, right? That is ensured by this 1 minus. right? So now you can understand that if you take all the entire expression into account for the discriminator, you should maximize this, and when you maximize this expression, you are inherently minimizing this d of g of z, right? Because d of g of z is so close to fake. Okay. So so this is how the discriminator looks at this entire thing. Now we'll have to think of how the generator performs. So what does the generator want? The generator wants, so the real images are not in the hands of the generator at all. So you can see that if you go by the arrows, there's no connection between the, did something happen? Okay. Yeah. Oops, where were we? Yeah. Yeah, there's no distinction between the fake images and the, sorry, where was I? Yeah. So the generator's job, like I said, it is to basically ensure that the fake images are as realistic as possible. Hence, what you want is that this part, whatever fake images are, discriminator's value should be as high as possible. So this entire expression, while this was getting maximized for the discriminator, for the generator, it will get minimized. So like I was saying that the generator has no link with the real images. They are independent. So the first term doesn't really care about the generator. I mean, generator doesn't really care about it. It's the second term that basically it cares about. So it tries to ensure that d of g of z is as high as possible. It wants to take that towards the real, predictions. Real some an image is predicted as real if its predicted score is close to one, right? So that is what the generator tries to do. So a maximization of this expression, the second expression, leads to just that, right? So this is how you can see that in the second term, the discriminator tries to maximize this expression, and the generator tries to minimize this expression. Right. So, like I said, that it's kind of as if the reward for these two are like playing in the opposite way, right? So conceptually, it's as if the reward for the generator and the reward for the discriminator are complementary. So one is the negative of the other. So this is how through a game you are. What is your end goal, by the way? The end goal is that given this generator, you want to learn such a good mapping from this latent noise vector to the image space that the images are very good quality. They are as realistic as possible, such that the discriminator now is fooled to uh, yeah, it's completely fooled. Okay, okay, right. Okay, so a few more loss functions that are generally used for the GAN optimization. So it's basically the Jensen-Shannon divergence, right? So this is the J's divergence loss that we were talking about, right? So that is given by, so it's J's divergence loss is nothing but a symmetric form of the KL divergence loss. So, for example, if you take this scale term that I'm pointing out between PD and PG, right? So, if you invert these two, KL of PG and PD, that is not equal to KL of PD and PG, right? So, in that way, J's divergence is like symmetric loss, right? So, it basically ensures that your P of data, the true data distribution, and the generator's distribution should be as close as possible. Okay, so that is what you want at the end of the day, right? That the generator's distribution, whatever distribution it generates, that should be as close to the p data as possible, so that the police or the discriminator is fooled, right? So yeah, I mean the GAN paper itself is pretty detailed on it, and in the class also these losses have been covered in great detail. So we can move on. The ultimate goal from here that we want to achieve is uh, that your generator should be a good approximator of the true data distribution. Hence, in the inference time, now you do not need the police anymore. So your end goal should be to make the generator as good as possible, but I mean, obviously, you cannot make the discriminator poor or bad for that reason. I mean, the better this is, the better this will get, right? So in the inference time, all you need to do is you need to sample some z noise latent vector from a 0 1 0 I Gaussian, right? And then send it to the generator, which will generate an image from for you, right? So this is only required in the inference time. Just one thing to be noted is that GANs, so like 2 points maybe. One is that GANs, while they generate very good images and they have been the de facto standard for the last maybe 8 to 9 years or maybe 7 to 8 years, they are incredibly hard to train, so there's a lot of stability issues, etc. That is point number one. Point number two is so this is just a very simplified uh, optimization of the GANs. So this is for the vanilla GANs. Vanilla GANs means this is the only part, this is the entire GAN, but there are other GANs also, which so based on your application, different architectures came up, different other loss functions kept on adding to this architecture and so on. Like cycle GAN is there, big GAN is there, and lot of other GANs. So style GAN is very popularly known. So it's basically a style transfer, some model that transfers the style of the training images to the other images. So all of them have many other components that can be looked at, right? So this is just a vanilla form of the loss function. Um, Okay. So, like I said, GANs are the like have been there for for quite some time. Before GANs, or rather alongside GANs, uh, in the generative paradigm, we had something called variational autoencoders, right? So, which is again very popular to even this day. So, a lot of researches are still going on here, and people are like, so there are now three things in the market, right? One is GAN, one is VAE, this variational autoencoder, and the other is the diffusion model. So, kind of like a competition goes on between among all three architectures, and currently the diffusion ones are becoming more popular. But yeah, I mean, a lot of research is going on in this direction as well, variational autoencoders. So before going into variational autoencoders, we have to understand what is basically autoencoders. So before the variational term came into being, right? So what we are trying to do in autoencoders is simply this. Again, it's an unsupervised method. There's no why. It falls under the generative models. So autoencoders are simple feature learners. Okay, so it says that a typical image is a very high dimensional data, right? However, not all parts of that image are equally important for, like, they are not equally informative. Many parts or most parts of the image do not contain any relevant or important information at all. So it is said that this high dimensional data, so you can basically represent it using a much smaller dimension. Okay, so that is what autoencoders do. So they take a training data X, right? They use an encoder which will convert or reduce the spatial dimension of this X. So suppose this was 224 cross 224 cross 3, and now you're converting that entire big chunk of data to some space of maybe 128 dimensions. So you convert it into a vector of 128 dimensions, and basically you are trying to say that this 120 dimensional data is enough to encode the entire information in the image, right? So how do you train autoencoder? So this is not mentioned here, but it's pretty simple to understand. So maybe I'll just try to do it in words here. So you have a training data X, you pass it to an encoder. So like it's a neural network which converts this image X to some dimension, some 120 dimensional vector. Now, how do you ensure that this 120 dimensional vector is a good enough approximation for the training image? So now it's a good enough approximation. If so, I generated this 128 dimensional vector. Suppose let's call it Z. So I generated the Z from the X, right? So now the what we can do is, to ensure that the generated C is a good approximation of X, we can make sure that we can generate X back from Z once again. So it's like a two hop or a cyclical approach. So we go from X to Z and Z to X, right? So X to Z happens through an encoder, Z to X happens through a decoder, right? So ignore these mu, sigma, whatever terms you are seeing for now. So we are only talking about autoencoders. We want to do is we want to learn an approximate feature vector for this high data dimension X, right? Such that this Z is able to model the most important information that is encoded in X, right? So how do you do that? So, like I said, there's an encoder which converts X to Z. There's a decoder which converts Z back to the X space once again. And to ensure that the true X and the generated X are pretty close to one another, you uh, um, basically put an MSE loss between this true X and the generated X so that they are as close as possible. So you are basically ensuring that Z is some like representation of the training data that is able to encode the information that is there in that entire 224 cross 224 cross 3 image. That is what is known as, wait, yeah, that is what is known as autoencoders. Now, coming to variational autoencoders, what we want here is that instead of using just any Z, right? So, in the autoencoder part, we were just you can say that we were trusting the encoder entirely to generate any Z, and from that Z, we were trusting the decoder again to go back to X, right? That may always, so ideally at the end of the day, we want a good Z that would represent X, right? So this formulation may not always lead to very good very good Z vectors. So now in variational autoencoders, the idea is very similar. All that we do is we attach a prior on Z. Okay, so instead of predicting Z, I'll try to predict I'll try to generate an approximate distribution once again, which is given by this Q phi Z of X. So Z given X. So given an X, we are trying to generate the Z. So to do that, we are trying to predict its parameters, right? That is given by the mu Z and sigma Z, right? And now, basically in this encoder, we are trying to predict these two quantities. So we'll have some code walkthroughs also today very quickly to understand, to just see this in terms of code. But we are trying to predict, instead of Z directly, we are trying to predict mu and sigma Z, right? And then we are trying to generate Z or sample Z from a normal or Gaussian distribution with mean as mu Z and covariance as sigma Z. So this looks like X, but actually it is Z, right? And now what we'll on the decoder side, so now we have sampled a Z. So this Z will be sent to the decoder, and the decoder's job is also again very similar. It will generate a mu X and sigma X, and you can understand now that you will generate your X from the Gaussian of mu X and sigma X, right? So instead of having a trusting the encoder fully to generate a Z and then again trusting the decoder fully to generate back X, you are just trying to estimate the parameters of a prior distribution, and you are from there you are sampling both Z and X tilde. Okay, so normally, like I said, in autoencoders, not the variational version. In autoencoders, I said that if you have an X and predicted X tilde or X hat, sorry, yeah, this is X hat, then the loss function is given by the true X. The This is okay. This is again we have by mistake we have exchanged these two. So this is like the predicted X, right? It's the generated image minus the true image and the MSE score of that. It doesn't really matter what is there in what order. So because it's a square function. So anything can be, I mean, it can be 2 minus generated or generated minus 2. I hope you get the point. So this is the original loss function in autoencoders, right? But in VAs, we use something called evidence lower bound, and we try to maximize it because we are trying to now play. We are playing in the distribution scenario, right? So we have what we have is not only the reconstruction loss that we can see here. So this MSE loss is what is also called as reconstruction loss. This we are trying to predict, but alongside that, this one that we are trying to approximate, we'll basically try to bring this distribution as close to the prior distribution as possible, right? So Z has a prior distribution attached to it. Again, like I said, that with the limited amount of samples, just finding a the true distribution of Z is not trivial at all. So we take this, we assume a Gaussian prior on the Z, right? And we want this QZ, the QZ given X here, that should be as close to that Gaussian prior as possible. Hence, KL of QZ of X with respect to P of Z, where P of Z is given by this unit Gaussian. Okay, so what we are trying to do is we are trying to make the QZ of X, which we are actually using to predict the Z, to be as close to the zero I Gaussian as possible. So these are the two loss functions that we have. Okay, and the data likelihood is bounded by this. So there's a proof for it which you can go back and look at. But the point is that the actual data likelihood is bounded by this, right? And if we maximize or yeah, if we if we optimize this, then if so, optimizing this is equivalent to optimizing this, right? So this is simpler to optimize. So this is not intractable, whereas the other maybe finding the data likelihood directly may be intractable. Okay, so moving on, some very simple questions once again. Okay, some some very simple questions once again. So if you are given the average of the latent vectors corresponding, so let's read this question once, and it's a very simple question, and it'll give you some feel of what we are trying to do. If you are given the average of, suppose you have latent vectors, right? Okay, and one of the latent vectors corresponds to men with hat, okay, and that is given as V1. Then there's another set of latent vectors that corresponds to men without hat, okay, like the approximate latent vector for men without hat, that is given by V2, and then women with glasses is given by V3, okay. Now, which of the following is the most probable generated image with the latent vector V1 minus V2 plus V3? Okay, so yeah, so this is how to find this. So yeah, I mean, this is a very simple question. So consider this men with hat as men plus hat. Okay, so V1 is men plus hat. V2 is what? Men without hat, meaning men minus hat. Okay. Now you are trying to subtract V1 minus V2 here. So men plus hat minus men minus hat. Right? So the two men are getting cut, they are getting eliminated, and all you are left with is the hat part. Okay. So you have this V1 minus V2 basically eliminates the gender information, and it only leaves you with the hat information. Now you have this women with glasses as V3, right? That is what we are seeing here in the question. So now you have this hat information and you are adding women with glasses, right? So women with glasses and this hat. What would that result in? That results in woman, which is the correct option, man with glasses without a hat, woman with hat without glasses, man with hat and glasses, woman with hat and glasses. So the fourth option would be the most correct one, because This V1 minus V2, like I said, if you can follow my cursor, it's referring to the hat, and V3 is adding the information of the woman with the glasses. So you are left with hat, woman with glasses and hat. Right? So option 4 is the correct option. So these are all like um, very simple questions to test your understanding of the vectors. So yeah, maybe they'll be useful. Okay. Now, one thing that we missed telling here is that one other, yeah, in order, so you understand that this is your entire network, right? And your Z is sampled from this Gaussian distribution, right? Now, in order to like train this model, so this is your loss function, the reconstruction loss and the latent prior loss. So you can understand that they have to be in order to like so this the forward passes from x to x hat, right? So the backward passes from x hat to through the decoder to the encoder. Now, um, what is happening is backpropping to the decoder is easy, but now you are sampling your if you need to backprop into the encoder, you know need to go through this Z, right? And this Z you are sampling from a distribution. So finding a gradient with respect to that is again very difficult, right? So what you instead do is you avoid sampling Z directly, okay, and instead you take a epsilon, which is so this is the reparameterization trick in VAE. So again, you can go back to the lecture notes. So instead of sampling Z directly from a Gaussian, you take this Gaussian parameters and you add a 0 1 noise with it. Okay. So if you so this 0 1 sorry, so this noise is actually sampled from the 0 1 Gaussian, and you have already found this mean and variance. So now going by simple probability tricks, your Z finally, instead of sampling from the Gaussian, it finally becomes mu plus sigma times epsilon. This epsilon you have basically, yeah, this epsilon you have basically generated from the 0 1 Gaussian, right? So you can go back and revise your probability classes to find out why this is true, right? But this is how it works. So based on the parameters that you already predicted and the epsilon that you generate from the Gaussian, it is simple to find out the value of Z. Okay, so the question is now what? In a VAE, if the encoder outputs mu and sigma, so they have given some mu sigma value as the final predicted value and some epsilon that has been sampled from the 0 1 Gaussian, and that epsilon's value is also given. Then the latent, what is the latent value of Z? So it's very simple, just put it in this formula, okay, and you have your value. And finally, this is the, if you add all of this, you add, sorry, you multiply these two and add this, you get this value of Z, which corresponds to the option. Just give me a second. Yeah, excuse me. So this corresponds to the option B here, 0.64, 0.23, and 0.42. Okay, so last part of the theory. There are failure cases for GANs and VAEs, and these are at least till the arrival of the diffusion model. Uh, these were the most difficult parts of training, where which would trouble the researchers the most, right? So when can they fail? Suppose your true data distribution, instead of being a single Gaussian, has like multiple modes, right? Anyway, we do not know the true data distribution, but suppose it is something like this, so it has multiple modes. Okay, so now we have seen, or we know that VAs basically they like optimize the maximum likelihood criteria, right? And that basically generates this green distribution, right? Which is completely different from the true data distribution. So VAs fail here. And GANs, while they try to model these two modes, what they do is they end up modeling only one of them. Okay, so the GAN learns a distribution which is close to this. Okay, And it that means what? That it ignores this mode completely. And imagine if there are multiple 10 such modes, then it's only looking at one such mode. So what that results to is something called mode collapse, where suppose if you're generating images of flowers, right? Different flowers. You would want ideally maybe one rose, one lotus, one sunflower, and all those different images you want. But because the GAN is fitting on this mode, in on this particular mode, the images that you'll get that the GAN generates are very close to one another, right? Which basically is unable to model your actual data's distribution. So this is what is known as mode collapse. So these are some of the failure cases of GANs and VAs, right? So given that we have covered whatever we had to do in the theory part, we'll go on to the coding part now. Okay, so this will be shared with you by tomorrow. So this notebook that I'll share with you. So this is primarily on autoencoders and variational autoencoders, right? So it's better to have a go through it because autoencoders, GANs, still kind of okay to understand GANs because of the min-max game that goes on between the adversaries. But yeah, autoencoder and variational autoencoders can be a bit confusing. Hence, I'm sharing this notebook with you. So please go through it and try to understand this fully. So you can see again, like we have put all the theory information here for you to understand very well what is going on. So we'll just again so we'll start with the motivation part. We'll go through this a little bit for a little while, the theory part, and then we'll move on to the coding part. So like I started with this when I started with the lecture video, I said that images are a very large high dimensional data set, like we have already like talked about, and this data set consists of thousands or maybe even millions of images nowadays, right? So like I said, that each image is made up of hundreds of pixels, and in real life, it's not only hundreds; it's much more than that. The order is much more. So each data point has many dimensions, right? So this is the main line in the entire variation in entire autoencoder world. So it states that real world high dimensional data actually consists of low dimensional data that is embedded in the high dimensional space. Right? If it is visible, this is exactly what I was talking about. That uh, real world data is very high dimensional, but actually it embeds very small information which is relevant or useful to us, right? So it consists of low dimensional data, that is embedded in the high dimensional space. So even in that high dimensional space, the information that we require is basically pretty low dimension, right? So that basically it says that even though the actual data might have hundreds of dimensions, the underlying structure of the data can be sufficiently described using only a few dimensions. And hence, this entire motivation behind creating or generating a small feature vector that would represent the entire image, right? So that can itself act as a generator itself. So you can generate new images. And oh, by the way, with autoencoders, you can understand since we are dependent on the autoencoder, on the encoder part, like maybe we can show this one more time. Yeah. So like I told that in autoencoder, not variational, we take the X, pass it through the encoder, get a Z, and this Z can be used to decode once again. So autoencoders, you can think of them as some sort of feature learner, right? It gives you the features only. Whereas variational autoencoder, since we have a stochasticity added to it, this can be used uh, once you get to know about these parameters. Once these are predicted, you will be able to sample the z from the Gaussian with the given with the like predicted mean and covariance, and that z can be So once you sample Z in that way, you can finally use the decoder to generate new images. That is why VAEs are so important, such important tools for generating new images, right? So there's a lot of theory here, so maybe you can go through it on your own time. But the moral of the story for a normal encoder is like this is the image that I was looking for, that you have a high dimensional X, you have a neural network now which will convert this high dimensional X to something on the low dimension. So here from 4 we went to 2, and we also have another opposite neural network which will convert these two dimensions to the back to the image space, which is here given 4 dimensions, right? This is the input is X. This two-dimensional layer is called the bottleneck layer, and it is denoted by Z, which is encoder. I mean E of X. E stands for the encoder, and now you predict an X hat, which is basically D of Z. So you run the decoder on top of the Z in order to generate this back. And now, in order to make sure that this Z carefully and correctly captures all the relevant information from X, you are basically making sure that X and X hat are as close to each other as possible. That is what is. So, in that way, autoencoders are very simple to understand. And below is a implementation for that. So, these are some of the import functions which you are used to now. But what is the encoder class now? So encoder, like I said, so autoencoders do not have any normal distribution or anything. All we need is we know by now that so here we say that this is applied on the MNIST dataset, and MNIST we know by now that it's a 28 cross 28 cross 1 image. So the total dimension, if you vectorize it, it's a 784 dimensional vector, right? So the encoder has two layers. One converts this 784 to a 512, and the other converts the 512 to some latent DIMS. Let's imagine this. This is a variable that we have the choice of setting, right? Let's imagine this to be 128. So we are going from a 784 dimensional space through a small neural network to a 128 dimensional space, right? So that is exactly what is happening in the forward function also. So you first take the image, which is 28 cross 28, flatten it to convert it to 784, and then uh, add the ReLU layer, add the linear 1 layer, which converts your 784 to 512, add the ReLU on top of it to add the non-linearity, and then finally return self.linear 2, which is like the yeah, which is like the 128 dimensional vector. Similarly, decoder also is very simple. Okay, so decoder's input is that 128 dimensional vector. So you are going backwards now. So you start with 128, go to 512, then from 512 you go to 784, right? And that is what happens in the forward function as well. So you have a self dot linear, you pass z through the self dot linear one, which converts it to a 512 dimensional vector. To add the non-linearity, you pass the ReLU, and then you do this. Okay, so you now generate back the 784 dimensional vector, and yeah, so now you are reshaping it to 28 cross 28 images, right? Finally, very simple. So your autoencoder class will consist of these two things, the encoder and the decoder, right? And you pass, so like for example, given an image X, you pass it through the encoder to generate the Z, and again, you pass the Z through the decoder to generate back the X hat. Now in the training function, it's very simple. So you initialize an optimizer, which is Adam here, but you can try others also, no problem. So now you have this X hat, which is the predicted or the generated X, which is passed through this autoencoder object, right? And the loss function, like we said, it's an MSE loss between the true X and the X hat. Okay, right. So where were we? Yeah. Yeah. So it's an autoencode. So basically, it is the MSE loss between the true x and the predicted x, and that is it about the training function. So now here, basically in this block of code, they are first downloading MNIST, so you are probably pretty used to it by now, and then training the model, right? So at the end of training, we are also doing one plot. Okay, so go through the code on your own. So here, what happens is in MNIST, we know there are 10 handwritten digits, right? So what they're trying to do is they're trying to plot the Z that we found, the Z that we obtained, okay, in the encoder part. Sorry, here in the encoder part, we obtained a Z, right? So given by this. So they are trying to plot that z and then trying to see like how it looks like. Okay. So here you can see that this blue color, it corresponds to all images in the zero digit. Uh, this color corresponds to all digits in the eight. Sorry, all images in the having eight digit, and so on. So you can see that the colors are based on the digits, and you can see that same similar digits, or like the same digit images, are pretty close to each other, right? So there are clusters that you can see, all the oranges are together, all the blues are together, grays are together, and so on. So in that way, it has automatically been able to learn the information with respect to the classes also, right? So the Z that it learned through this entire autoencoder training, that already comprises of all of this information. The class information has already gone into it, and it has been able to generate clusters. However, if we look at it a little bit critically, we'll see that while this cluster, the orange, the gray, these are well formed clusters, there are some mixtures here, like, right? So the six digit, or the corresponding to the pink one, or three corresponding to red, or maybe brown, which is corresponding to five, they are all kind of like clubbing together. Oops. Yeah. They are all kind of like clubbing together, right? So now, yeah, these are some of the reconstructed images based on yeah, yeah. So what they have done is the they have plotted the latent vectors. So first of all, we see that the as a result of this plot, we see that the latent vectors cluster similar digits together. Okay. Next, what they have done is they have sampled uniformly from the latent space and seen how the decoder reconstructs inputs from arbitrary latent vectors. Okay, and you can see that these are the generations of the different images. So the code you can look at on your own time maybe, but yeah, I mean they have basically tried to show you the reconstructed images from arbitrary latent vectors as given here. So they look pretty realistic, but some of them are not as clear, right? So for example, this one, is it a 3 or an 8? We don't know, right? So this one, is it a 0 or a 7? We don't know. This is a 7 or a 1? We don't know. So while many of the images have been created very well, not all images are as good, right? So now, then next comes the variational autoencoder part. So like I said, job is 2. So here, um, okay, yeah. Cool. So, yeah, here there are twofold activities. So, one, like small mistake is here. So, from the x, you are supposed to predict the mu of x and the sigma of x, right? This mu should be sigma. So, that is a typo sort of. So, you are predicting these two, sampling z from a normal distribution with these two as the parameters. And this from this z, you are getting your X hat back. That is the only difference with the actual autoencoder. So this is the variational part where you are introducing this stochasticity. You are assuming all these prior information on the latent Z. You are restricting Z, and you are just not letting a encoder decide what the Z should be. You are restricting Z. All you are doing is you are predicting the mean and the covariance. So this is the covariance, like I said, and you are generating Z automatically from the normal distribution based on the mean and the covariance that the encoder predicted. So the variational autoencoder is a little bit longer than the normal autoencoder, but it's pretty simple to look at. So you have a linear layer, which again this part is the same. Linear 1, 782, 4 to 512. Linear 2 is 512 to latent DIMS. Okay, so this is the part which where we are. So this linear 2 is the part of the network which is taking you to the mean vector through which you can predict the mean vector. And here, this is where you are predicting um, the covariance matrix, right? And also, like I said, that we do not, in order to make backpropagation easier, we do not sample z's directly from the Gaussian. Rather, we find its value using uh, an epsilon, which is a 0, 1 Gaussian, right? So that is what is done here. So self.n is a normal distribution of 0, 1, right? And what you do here in the forward function is the first step is to flatten. The second step is similar as the autoencoder, right? The third step is to generate the mu. Fourth is to generate the sigma. Then, like we gave the formula that mu z should be mu plus sigma into uh, some sample from the 0, 1 Gaussian. So the 0, 1 Gaussian was initialized here, and this is z is finally mu plus sigma into this self dot n dot sample uh, from this 0, 1 Gaussian. So you are sampling um, some epsilon of the correct shape. I'm not going into the shape part, and you are generating this z. Finally, you are encoding the loss function here, right? Which we described back while back. Okay, so this is the yeah. So this class is called the variational encoder. Okay, so this is the finally variational autoencoder class. Okay, so it has an encoder which is the variational encoder that we saw above, and its decoder is the normal decoder class that we saw like somewhere here. Yeah, it basically converts from the Z, directly converts your image. Yeah, we were here, right? Now the training happens in a similar way. So like we in the elbow part, so again going back here, so to the actual loss function, yeah, we had two losses. One is the reconstruction loss and one is the KL loss. So we had already calculated the KL inside the object, if you remember. And now in the loss we have this MSE, the reconstruction loss, and the KL loss. So these two we are jointly minimizing in order to kind of like maximize the data likelihood. So that is the bound that we were given, right? And now here, these are the clusters. So if you go back and see, so again, these clusters, I mean, there are some mixtures, but they are much more compact. If you go back and compare this cluster with the previous one, you'll see that they are much more compact than the previous clusters that we saw. There's still some amount of mixing that we could not stop, but these are better quality clusters. Again, with respect to the digits. And again, we are plotting the like reconstructing the images from the Zs that we kind of like um, yeah, which we sample, and these are the images that we are getting. Again, not all of them are very clear, but if you compare with this, so this is the variational autoencoder. There were many confusion points. This has reduced to a large extent. So now you can more or less make out most of the images. Maybe not all of them are very distinct. So here, some of them have problems. Here, for example, what is this digit? We do not know. But the problem would have reduced to a great extent, right? So there is an extra fun section. So again, this is for you to have fun with this particular all these assignments. So this notebook I'll share with you. Please go through it and play around with it. So especially in the generative modeling, I think it's a good idea to uh, play around with these codes. So remember, they are very vanilla sort of autoencoders and variational autoencoders. So now much more sophisticated models have come up. So maybe you can try with some MNIST and some simple data sets to see how good clusters you are getting, right? Trying to find out, like, so you can see that here the clusters, uh, the plot starts from 5 to minus 20 and minus 10 to 15. Whereas in the variational autoencoders, they have become much more compact. So the scale has reduced a lot, and so on. So all these advantages are there. So just try to find out on your own what is going on here. That is the best way to learn. And yeah, and this extra fun part that has been given here, so that is for you to have that extra fun basically. So play around with it. So I think that will give you a very good feel of what goes on exactly. So I hope this kind of gave you the coding part, especially because the theory is not very easy to grasp. The coding part will give you some more idea to clear some of your confusions that you might still have after the classes. So it will be a good idea to go through them. So yeah, pretty much this is what I had to cover. So very less number of students somehow today. Um, yeah, hopefully we'll meet next week then. Thanks.